Okay, so we're going to work on a problem trying to work backwards. We're given information about an NMR spectrum. So we're given C7H16O4, and we're told we have a peak at 1.93. That is a triplet that has a coupling constant of 6 hertz. We have a peak at 3.35. That's singlet. We have a peak at 4.49. That's a triplet with a J coupling constant of 6 hertz. Coupling constants, remember, tell us who's talking to who, right? If I couple you, you're going to couple me in the same way, so we'd have the same number of coupling constant. And the relative ratio of protons is 1H to 6 H's to 1H. That's the relative ratio. Does that mean we always have just one proton, 161? No, it's a relative ratio. We could have 2, 12, and 2. We could have 3, 18, and 3. Right, so it's a relative ratio. What's the first thing we need to do? What's the first step in all these problems? If you're given the molecular formula, what do you need to do? The degrees of unsaturation. You got to figure out if you have any pi bonds or rings, right? You have to figure out if you have any pi bonds or rings. So if we do the degrees of unsaturation here, what do we end up with? So it's 2 times 7 plus 2 plus the number of nitrogens minus X minus H. We divide the whole thing by 2. So what do we get here? Do we have any nitrogens? So that's 0. Do we have any halogens? Fluorine, chlorine, bromine, or iodine? No, so that's 0. So 2 times 7 is 14 plus 2 is 16. How many hydrogens do we have? 16. So 16 minus 16 is? 0 divided by 2? 0. Pull out your calculators, you sure? I'm kidding, please. It's 0. So the degrees of unsaturation is 0. So do we have any rings or pi bonds? No. No rings or pi bonds. All right, so that's good. That gives us a piece of information. So the biggest thing when we work these problems is if you're on the test, you want to make sure you write down your thought process. If you write nothing, I can give you exactly 0 points for that. Right? If you at least do the degrees of unsaturation, I can give you some points. Right? You've earned some points. You've thought at least you have a strategy to begin this thing. Same way, absolutely. Yep, we'll both agree the same way. Okay, so the tricky part here is coming up. So we need to look at a triplet. So what does a triplet look like? That's going to be 3 peaks, right? And it's worth at least 1 hydrogen. So we say, so the triplet there. And it's at 1.93. Is that very shielded or de-shielded? It's pretty shielded, right? So it's not next to something that's probably really electronegative. All right? We know it's coupled, though, because of the coupling constants being the same. It's next to another triplet. But this triplet's at where? 4.49 ppm. Is that very de-shielded? Yeah, so let's look at our tables. Something around 4.5. What would that proton be next to, possibly? A halogen, but we don't have any halogens. An oxygen, right? We pull our table, so if I have an oxygen, that must mean I have something next to it, right? At least one H, right? Next to it, that's being de-shielded because of it. This is a carbon, but I don't know what's bound over here. Actually, to take a step back, do I know what's bound over there? Let's think about that. This H at 4.49, right? This H at 4.9. How is it split?
3 ways. So
It's split into a triplet, so how many nearest neighbors must it have? Two. So it must be next to another carbon with hydrogens on it, right?
But those two are the only ones that are coupled with each other, and the other one have two, or do you not know that?
Don't know that yet. So, what we know is our peak at 4.49. And we think, all right, so let's take a step back. And ask ourselves another question. I don't think we're as clear as we should have been. So a hydrogen next to an oxygen, is that really going to be at 4.5? So we don't know what's on this side of the oxygen. But what's really going to be here? Is 4.5 pretty de-shielded?
Yeah.
Maybe there's another oxygen over here. I think the range is usually 2.5 to around 3.5 for something next to an oxygen. Right? It's not as de-shielded as say a halogen would be.
Double bonds make a difference for the oxygen. The oxygen's double bonded to the carbon.
If oxygen's double bonded to a carbon, that'll make a difference, but not in this case. So the point I'm trying to bring up here is, if you have one oxygen de-shielding you, is two oxygens going to make you even more de-shielded? Yeah, so it's kind of an additive effect. So a 4.49 is really de-shielded. So that's why I'm thinking this hydrogen has to be next to two oxygens. That's really downfield. Okay? The other thing I think we need to think about is we have 7 carbons here, and how many peaks? 3, and 16 hydrogens. That should send off a signal in your head. This molecule is probably it's very saturated, but if I only have 3 peaks with 16 H's, symmetry. Think about symmetry. This molecule is probably very symmetrical. Right? It's probably very symmetrical. So I don't know what's over here yet. But I know this hydrogen right here, that's probably at 4.49, has to have how many nearest neighbors? Has to have 2. Right? Has to have 2 to be split into a triplet. The other thing we could go back and look at is we start out with 16 hydrogens. When we're given this relative ratio of 1 to 6 to 1, if we take that times 2, we get 2, 12, and 2, right? Does that add up to 16? Yep, today it does. Right? So that's probably the actual ratio of our hydrogens. Right? So let's change it to now to being that ratio. So now the proton that's here, we need to find another proton that looks just like this one. Right? It has to be just like it. Right? Because I have to have 2 now, not just 1. For these protons, I have 2 already. Do you guys see the 2 I already have done? Right, so they're already there. So how can I make it so I have another H just like this one? What would I have to do? Make it exactly the same on the opposite side, right? Have to be exactly the same on the opposite side. Let's see if I can erase. Of course not. So over here, I must have an H, right? Because now these 2 H's that's circling in blue have to be exactly the same. So there's another oxygen there, another oxygen there. And I still don't know what's on these sides, right? So let me draw it another way. Let me draw it a little clearer maybe. So we have here is a CH2. There's an O. I don't know what's over here. There's another O, and I still don't know what's there. This is the H that's at 4.49. So it's the same H there. On the same side, right, after the same motif on the same side, this molecule is symmetrical. There's another H that is exactly the same as this H, right? And then there's these 2 CHs right here as well. You see that? Do you see the translation between from here to here? So if I labeled these, if this was 1 and 1, and both these guys were 2, the 1s are right here. This guy and this guy are both 2s. Does the splitting match up? They both be triplets, right? With 2 nearest neighbors. We're going to see how these H's have 1 neighbor, 2 neighbors. So it splits into a triplet. So what do we have left to worry about? We have a bunch of singlets at 3.35 worth 12 hydrogens. So what do we need to add in? You just need to add in CH3s. Right? So the final product then is going to look, let me just do another slide. We had our H here. We have another H here. And these 2 H's. All right, so the real key here was two things. And these are all methyls. The key here was really having to think about the chemical shifts, right? And understanding where the chemical shifts are at. If you're getting deshielded by 2 oxygens, you're going to be much more deshielded than you'd expect, around 4.5. That was the key trick here, was realizing this 1 hydrogen was at 4.49. It must have been attached to something, it must be really close to 2 oxygens. And then also seeing the splitting, seeing those are triplets and they're coupled to each other. The other thing was, of course, the symmetry. All right, seeing that symmetry element. So do you see how these last 3, these 12, 3, 6, 9, and 12 protons are all exactly the same? Because this molecule is symmetrical. This is a tough one. So we're going to do another problem from the homework. C6, H12, O2. It gives us IR information. It says there's a peak in the IR at 1743 wave numbers. It actually shows the NMR spectrum to us. So I'll just write down the numbers for us. For HNMR, it's saying there's a peak at 4.1. That is a triplet with a coupling constant equal to 6.7, and it's worth 2 hydrogens. There's another peak at 2.1. That's a quartet with a J coupling constant equal to 7.6 hertz. That's worth also 2 hydrogens.
And what is worth 2?
So have another one at 1.7. That is I would say it's a sextet. Same type of coupling constant, right around 7.0 hertz. It is worth 2 hydrogens. That's the area, that's the integration. There's another one at 1.1 that is a triplet, a T coupling constant equal to 7.6. And this is worth 3 hydrogens. And then finally, there's another peak at 0.9. That's a triplet. Coupling constant 7.4. 7.4 hertz. And it is worth 3 hydrogens. All right? So how many different types of hydrogens does this molecule have?
Which ones are 7.0 and which ones are 7.6?
Essentially, all these coupling constants are basically the same. So most of these protons are talking in a similar manner to each other. So the coupling constants might not be that useful here. All right. So how many different types of signals do we have? So how many different types of protons must we have? So we have 5 different protons, different signals. Degrees of unsaturation. So for degrees of unsaturation, we have 1, which means either 1 pi bond or 1 ring. All right. What does the IR tell us? Look at your IR tables. What is that? What range is that? A C double bond O. And if you look closely, it even tells you exactly what type of C double bond O. We mentioned this in class. This C double bond O has a higher frequency, so it's harder to stretch. What is this C double bond O? Specific type. It's 1745. I wrote it on the board in green, the right side of the board. It's in your notes. It's on the PowerPoint slides. 1743 is particular for an ester. Right? So it tells us this much. This is what we've gathered so far without even looking at the NMR. We know there's 5 different protons. There's 1 degree of unsaturation. And we have an ester. Right? So this ester, we don't know anything else about it. We know there's a CO2, right? The ester. Does that take up our degree of unsaturation? Yeah, so that's covered. Check that off. So the other thing I like to do as I'm working these problems, I like to have the molecular formula here to make sure I don't forget any hydrogens or oxygens. So I just start subtracting out things. So what have we just subtracted out? The CO2, right? So what do we have left? We have C5H12 left, right? Now we got to look at the NMR and start piecing this together. Right? Now we got to look at the NMR and start piecing this together. So our strategy then would be, we're going to take a look at the most de-shielded proton signal, and we're going to assume the most de-shielding site is the one on this side of the ester, because this is the one that's closest to the oxygen. If we look at our tables, right, just like we did the last problem, if you're a hydrogen over here next to a carbonyl, you're around 2. If you're next to an oxygen, you're around 3, or even higher, right? 4.1. Okay? So what piece should we put over there? So if I'm saying I'm going to have a CH2, right? Because how many hydrogens is the first thing at 4.2 worth? Worth 2 hydrogens, right? So I draw a CH2, and I know it's already bonded, right? It's on this side of the carbonyl. I still don't know what's over here yet. What's the splitting of this peak at 4.1? What's it splitting? It's a triplet. So how many nearest neighbors must it have? 2. So it has to be next to another CH2, correct? I still don't know what's over here. So what can we subtract out now? We've added 2 more carbons and 4 more hydrogens to our thing. So we can say, let's take out C2H4. So now we're down to C3H8. Okay? So this CH2 was a triplet. What would we expect? So now we got to pick another peak. What other peak do you want to look at now? Do you want to look at? There should be something that kind of sticks out like a sore thumb. Let's look at the next most de-shielded thing. What's the next most de-shielded proton? It's at 2.1. All right. Now, what would that most likely be next to? Look at your table. That's not as de-shielded as next to an oxygen, but it's de-shielded to be next to
The carbon connected to
the adjacent to the ketone. So that would be a CH. These CHs would probably be next to a carbonyl because they're at 2.1, right? So that's de-shielded. That's where protons that are in this position would be at, 2.1. Now, how is this guy split? This peak at 2.1, how is it split? So how many nearest neighbors must it have? Okay. Well, let's draw CH3 next to it. Does that match up? Is there another? So if I draw CH3 here, how will these CH3s be split? In 2A? How many nearest neighbors do these CH3s have? How many nearest neighbors do they have? 2. So it'll be split into a triplet. Well, is there a peak that's worth 3 hydrogens that's split into a triplet? By God, there's actually 2. So one of them works. It doesn't matter which one at this point. One of them works. So now what can we subtract out now? We can subtract out C2H5, right? So all we're left now with is CH3. Do we have any other? What's the only spot we have left to put it?
On the other side.
On the other side over here. So now as a final check, let's go back through the whole thing and make sure our splitting makes sense. Right? So to do that, the best way I think to do that is actually to look at the molecule you drew and to analyze it independently without looking at the stuff they gave you. So these hydrogens right here would be split as what? A triplet worth 3 hydrogens. So we do see something like that. Good. These 2 hydrogens would be worth 2 hydrogens. They'd be around 2, right? Because it's next to a carbonyl. How are they going to be split into? A quartet. Still got that. Good. Got our carbonyl matching with our degree of unsaturation and our IR. We have another CH2 that's very de-shielded at 4.1, which means it's usually like next to an oxygen. That's split into a triplet, so how many nearest neighbors does it have? 2, so that matches up. This CH3 on the end, right, should be turned into a triplet when we see a CH3, one of these 2. Now what about this guy? How many nearest neighbors does this guy, these hydrogens have? 5, so it's going to be split into a sextet. Does everything match up? Yes. Now literally what I just said, if you wrote that down on a test, that'd be a good idea. Right? Write down what you're thinking. Absolutely. Let's take a look at let's look at a problem where they actually ask us to drag and drop the splitting and pick up the integrations. So this is an oldie, but this is an old favorite. This is this ester, right? It's an ester. How many different hydrogens will we expect in this ester? Probably. How many? 3. We have 3 different protons. We're all buying that. Fantastic. H, 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 and H. Very good. So let's go ahead and label them. I'll label these guys A. These guys can be B. And then we'll label these guys C. So let's look at H. How if I'm going to do it that way? Let's look at H. I did it again. HA with the red. So let's talk about HA. HA has how many nearest neighbors? 2, so it's going to be split into a triplet. It should be a triplet. How many protons is HA worth relative in this molecule? How many hydrogens is HA worth? The height of the peak will be 3. So it'll be worth 3 hydrogens within this one molecule. HB, how is HB going to be split? What's it going to look like? Quartet. How many hydrogens should HB be worth relative to HA? It should be a 2 to 3 ratio, right? Then finally, HC. How many nearest neighbors does HC have? None, so it'll be split as a single, not split at all. And how many hydrogens will be worth relative to A and B? 3. Good. Now, what's the final step? So when we do these things, we always say number of protons. We say the integration. We talk about the splitting. And what's the one thing we haven't talked about yet? Now the coupling constants, I'm not worried about that too much. The frequency, whether these things are de-shielded or shielded, right? We got to analyze that. So HA, so which one of these protons, A, B, this is still C. A, B, or C, which one's going to be the most de-shielded, and where would you expect it to be at, according to your table?
Downfield.
C would be downfield, but where would you, give me a range. Around 4 ppm. Good. Give me another one. What about HB is probably the next most de-shielded. Where do you think HB is going to be at? 2? Sure. Around 2 ppm. What about HA? Where's that going to be at? A little over 1 maybe. Perfect. That's what we're looking for.
And like
If we wanted to add another layer though real quick, so would HB and HC have the same, or would HA and HB have the same coupling constant?
Yes.
Yes, because they're coupled to each other. So they'd also have the same coupling constants as well.